Team, welcome back. We're now looking at the next part, the third video for matter. We're now looking at the shell theory. What does that even mean? So our focus really is looking at how electrons are actually organized into specific energy shells around the nucleus, okay? This is one of the simplified forms, and you will learn more about this if you decide to continue with chemistry, but we think of them as key shells. Now, there's different configurations for these shells as well, and we'll learn how to show the arrangement of the electrons. Number one, please watch this video, and I want you to answer, what can be found in the shells of the atom? As you may have guessed, it is in fact the electrons, okay? Electrons and a lot of empty space. This is another really great article to have a quick read up on, a bit of background and history about Rutherford and the models and the Niels Bohr coming in. And I really want you to focus in on this table here, where you can see for each shell, what is the maximum number of electrons in each shell. Please note it is the maximum, so you can always have less in the shell. And the arrangement we follow is we've got 2 electrons first up, followed by 8, and then 8 again, but you do have some cases where you can have more, and then the 4th shell is 32. So this is the actual arrangement that you will use when you're actually talking about where the electrons are located. And just please note the light blue words are the key words you need to focus on. Shell diagrams is something you'll learn to do. Valence shell refers to the last shell that you have in a given atom. The electron shells, again, we've talked about. The Bohr model is actually a way of representing this, and the electron configuration is actually numbering these numbers. So going 2 electrons, 8 electrons in the second shell, etc. So I'm going through this quickly. Please feel free to ask any questions or pause and have a think if you need more time. Now, to help you with the reading, there's also a few key questions on the next slide. In a nutshell, I'll go through the answers here. The name of the scientist who actually suggested that the electrons are in specific orbits, Niels Bohr. Why does it say the electrons fill the shells closest to the nucleus first? It comes down to the stability. Sorry, if you are not sure where I'm getting the answers from, it's all from this article in this paragraph here. So it says the electrons are normally located as close to the nucleus as possible because it's a lower energy state and is more stable, and the electrons fill them close to the nucleus outwards. Okay, and you'll later on learn why this happens, but it's about the stability. And it's nice and close. And remember, the protons are positive, the electrons are negative, and there is that attraction. And then number 3, the table to show how much electrons can fit into each orbital or shell was the one we focused on just up here. So please take a moment to copy the key things down and go and get nice and familiar with it. Now let's look at some diagrams. So this is a diagram that shows you the electron configuration of oxygen. And you may remember the first shell has a maximum of 2 electrons that you can see. I've then got to move on to the next shell, and that's where I put these. I've got a question for you. How did I know that oxygen has 8 electrons? Have a think. That's it. So the key idea here is that the atomic number of oxygen as a neutral atom is 8, and you may remember it's neutral, so it means it's also got 8 electrons. That's how I know I've got to fill the number 8 into this electron configuration, which we learned from this table here. So we got 2 first, the remaining 6 go into the second shell. Okay. Now just also note that we like to show them in pairs when possible, and that just is a nice way of representing the number of electrons. All right. Please note this is called the electron configuration. This is actually our electron dot diagram. Okay, there's 2 different words for it. And again, the outermost shell is called the valence electron. In this scenario here, can you have a guess? What do you think the number of electrons are in the valence shell? That's right, it's 6, as you can see here, and count on the outermost shell. And just another example really of calcium this time. Now calcium actually has 20 electrons, has an atomic number of 20. This means that we've actually got to allocate it into the 4th shell, because if you look at the first, there's a maximum of 2, maximum of 8, maximum of 8, and we have 2 more to make 20, so we've actually got to go into the 4th shell, hence how we've drawn it out in these shells as well. Just another example for you there. These questions and the shells, it's really important to do more exercises. So we've actually got 2 exercises here. I'll do one just in a quick nutshell for you. Number 1, you look at the atomic number on the periodic table for sodium, 23 from my memory, and how many electrons does it have? Same as the number of protons. Okay, then the electron configuration, you've just got to remember how much per shell, and you can write 2, 8, 1. And then you've got to talk about the valence electrons, which is how many electrons in that last shell that's been highlighted in red. Just the one. Same deal over here with your neon. And then you've now got to actually pick 4 elements from the periodic table, other than the ones we've done before. Use circles to show the electron shells, put the electron configuration underneath, and just put that here. So it should be very similar to these diagrams here, but have the electron configuration on the bottom, okay? And again, a nice table to bring it all in together. This time round, you're doing the name of the element from the periodic table, the symbol will be next to it, atomic number, and then this is just putting what we've worked out over here into just a table. We're putting what was in the first shell, second shell, and then you want to say how many electrons were in that last valence shell. Now for these ones here, where you don't actually have the element here, you want to count and see how many electrons are there. Because it's a neutral element, you want to say it also has the same number of protons. So what has an atomic number of 8? Oxygen. Okay, so you just work through it like that. And then some more for you to complete. By the time you've done this, you are well and truly on a good foundation for this. So really well done. And I'm just going to now touch base on a few key things going into a little bit more depth. We're going to look at what isotopes are in this next lesson. So if you do want to have a bit of a break and cut it here, feel free to pause and take a break. But welcome to lesson 6. For lesson 6, please make sure you do understand the foundations of what we learned previously about the atomic number, because we're now going to look at isotopes, which is where we have different mass numbers but the same element. How does that even work? This is going to account for one subatomic particle we haven't talked a lot about, our neutron. All right. So what you're going to find is usually for example, oxygen, you've got your protons there, but we haven't actually talked about the neutrons in quite a bit of depth. But what you will find sometimes is there may be one less or one more neutron than the number of protons, or a few more, and that does cause a bit of instability. But I'll stop yapping away. I'll give you a chance to watch this video. It'll help you understand that isotopes of a particular element have the same number of protons. This means they have the same atomic number. Isotopes of a particular element have the different mass number. This is because they have different numbers of neutrons. So please take a moment to watch that once or twice as you need. Now let's have a look at an actual example of the isotopes of carbon, for example. Okay, so first of all, you got to go back to your periodic table. What is the atomic number for carbon? 12. Okay, how do you know this? That is that smaller number that you find there. But note here, you've actually got carbon 12, 13, and 14. Yes, this is possible. You do not always see it on your periodic table, but these do exist. These are the more unstable versions of carbon. Okay, these represent the different mass numbers, and these are called isotopes because they are still the same element with the same number of protons. However, they have a different number of neutrons. Similar to the carbon situation, you've also got the same thing happening for lithium. All right, lithium and her cousins. I don't know what silly analogy you want to use to help you remember. So lithium here, the one we expect is here. Then you've got lithium with one extra neutron than all the protons. If you take a look, you can see the extra neutron there. And then you've got lithium with 2 extra neutrons, okay? You just have to state the number of neutrons here. Just count the brown dots, the brown neutrons, and you'll be able to tell, okay? Remember, to find out neutrons, you just have to subtract the atomic number from the mass number, okay? Going back to a really early lesson there. Same deal here with your hydrogen. You can also have no protons and an extra proton. Do the same here too. So I hope you're getting an idea of what's happening. So you've also got the same thing for our lithium and our hydrogen. Now this time around, you're now going to have a go at looking at different isotopes with different numbers of neutrons. So the student wrote all the atoms of the element that are identical, explain whether this is correct. So with our new understanding of things, we now know that elements, although they actually have, the same number of protons and the atomic number, they actually are not identical because they can have a different mass number, a different number of neutrons. So you've got to explain that in a full sentence, explaining that you can actually have more neutrons, but it is still the same atom, okay? Just a different isotope. Now, same deal here. You're now going to do the same thing with your oxygen. What's the atomic number? How many protons? How many neutrons do you have? And the amount of electrons, just as a nice foundation over here, okay? Now, another go at just kind of applying our understanding of isotopes. You've got some examples where algebra is combined with science. Don't worry, it's not that bad. We're basically using W to maybe call a makeup element, I don't know, Wilbert, okay, on Xavier, I don't know, I'm just making them up. But the key thing is they're asking, are these the same element? Is that possible? How do we work it out? We have to go back to our definition of what the elements have and what isotopes are, okay? Remember, elements, they have the same atomic number, same number of protons. So that means if they've got this bottom smaller number the same, they are in fact the same element. However, the top, the mass number, which includes the neutrons, can be different. So this line here, no, they are not the same element. Same here. And how about this one here? They all have 17, but this one's still got a 16 there. So you just got to explain which ones are elements, which ones are not, and why. All right, good luck with that one. Now, lastly, radiation. Well done for coming this far. It's a nice, interesting part which has a lot of real-life application. The reason I love radiation is it links really nicely into the isotopes, because you may remember I talked about the fact that these neutrons can actually be imbalanced and cause it to be unstable. Because let's say you've got 3 protons, right, and you're an isotope with 4 neutrons. That's no longer equal, and this actually releases radiation. So there's a few different, you will also learn about 3 things, your alpha, beta, and gamma radiation. Okay, and you'll be able to explain the impacts and how they apply in real life. So watch this really cool video that shows you about the 3 types of radiation, and watch it once more and complete the table on the next page. All right, this actually links onto things like nuclear energy, etc. It's quite interesting, and your microwaves. So I love this diagram here. It shows you how far alpha radiation can go, then your beta, and then your gamma. You can see they can even pass through lead. All right, so I just want you to write down, what is it? What is alpha radiation? What charge do you get? How far can it penetrate? Which is shown in the diagram. Your video will help you with that. Okay, now this is the interesting part. What are the impacts of radiation? Now I want you to think of, do you know or remember any examples of harm caused by radiation? Have a go, have a little think, and have a go at these questions. And you may want to also read on the right here, a really interesting article about the actual impacts of radiation, how we've got alpha and beta particles, which can actually remove electrons and cause these once atoms to become ions, and then these actual free radicals can then go off and damage other important things like your DNA, okay? So this actually is one of the things for cancers, things like cancer, etc. So it's a really interesting article to read, and I want you to have a go. What does radiation do to atoms to turn them into free radicals? You want to actually have a read in this part here. How can the presence of the free radicals in the human body lead to the development in cancer? Okay. And lastly, there's actually positive uses to it as well. We actually can use it in medicine for things like your x-rays, your radiation therapy, to actually kill off cancer cells. So please have a read of that, okay? Lastly, some 2 last videos to go over: how a gamma ray is produced, what effect do they have on cells, how they use positively, so we've addressed some of that already. And then lastly, isotopes of the same element have the same chemical properties. Relative isotopes are isotopes that are unstable, radioactive, sorry. And then you want to watch this video to help you finish the rest off, okay? It can be used as treatment to kill cancer cells. Good luck, team, and reach out for any help as you need.